Hi, I'm Chin-Long Tan. So in this summer, I've been trying to find evidence for deformation in gallium-70. My mentor for this project is Dr. HK. So let's start off with some theory. So here we are looking at the nucleus shell model. In the nucleus, if its number of protons or neutrons is equal to one of these numbers inside the red bar, which are the so-called magic numbers, then the nucleus has a spherical shape. The tricky thing about gallium-70 is that it has 31 protons, which is pretty close to 28. That tends to make the nucleus spherical. But it also has 39 neutrons, which is far away from both 28 and 50. That tends to make the nucleus more deformed. So can gallium-70 be deformed? That's the research question we try to answer this summer. Here is the same model, the nuclear model, but in a more general context. The beta 2 measures the degree of deformation in the nucleus. The numbers inside the circle represents the number of protons or neutrons of a nucleus, and the y-axis just plots the energy of the energy states. Each of these lines represent an energy state, and we are particularly interested in this region. And we can see that unless the nucleus of gallium-70 is deformed, otherwise the odd nucleons cannot occupy these G9 states. So if in quantum mechanics, only a deformed body can gain energy through rotation. So if the two odd nucleons of gallium-70 does occupy the G9 state, it will be deformed and it will tend to gain energy through rotation, whose energy we can predict using this formula. And based on this formula, we can see that if you increase J, we expect quite a constant increase in the kinetic energy. So the motivation behind this research is that we already have found an energy state that has a spin of 9 plus. So 9½ plus 9½ is 9. And also in the neighboring odd nuclei, we already have found the rotational band that start off at an energy with a spin of 9 plus. So how do we get our gallium-70? Last summer, in an experiment done at Florida State University, a carbon-14 beam is accelerated to smash into a nickel-62 target, and when they fuse together, they either underwent fast fusion where they got separated again, or they form a compound which is rapidly rotating and spitting out stuff. If it happens to spit out an alpha particle, a proton, and a neutron, we get our gallium-70. And gallium-70 produced in this way is in a highly energetic state, so it tends to relax down to ground state by releasing gamma rays whose energy and intensities are measured by this germanium array. So the method of filtering that we use is called gamma coincidence. The basic idea behind it is that every nucleus is produced in every 100 nanosecond. So let's say if we see gamma 3 in our spectrum, we don't expect to see gamma 4 in our spectrum because it would take 100 nanoseconds before that happened. And so using this technique, we can filter out our data. This is the full spectrum, and this is a filter spectrum, and we can see that it's much cleaner. Our results in this summary is that we have found 5 new levels, and the most important thing is that we have found a tentative rotational band which can prove that gallium-70 does rotate and could be deformed. So we have also done some interpretive calculation to see if the placement of these new levels makes sense. So far as we can tell, we can see that gallium-70, which is shown in red, follows the behavior of its neighboring nuclei and also follow the behavior of other odd nuclei. And this is another calculation that we have done. So far from these 2 lonely points, it still agrees with the other experimental results done on other odd nuclei. So there's still a lot of things to do, such as assigning spin to the new level of energy, and then we can also measure the parity of this spin. We can measure the gamma intensity. We can further enhance our level scheme, and lastly, make a lifetime measurement. Thank you.